Hello and welcome to Applied Infrastructure Sciences, first in a series of informational tidbits and facts. Today's topic will be an overview of non-reinforced concrete corrosion. I am Dr. Timothy K. Boone, and I am the Director of Formulations for AIS and also the Senior Scientist for Product Research and Innovation. AIS is committed to making infrastructure better, not only for today, but for the future. So what is the corrosion of non-reinforced concrete? It is important understanding the factors that contribute to this adversely affect corrosion, and the environment is very important to being able to understand what corrosion is and how it acts. We will not dwell on a lot of chemistry, but give you concrete tidbits of knowledge that you can apply. The interaction between an infrastructure and the environment to which it exposed is one definition of corrosion. The second definition that you need to be aware of and keep in the back of your mind as we go through this today is deterioration and disintegration of concrete can be a direct result, and usually is, of a very vicious attack by reactive gases and liquids. Unprotected concrete disintegrates very rapidly in acid pH environments and even in very basic pH environments over time. What types of structures are at risk? Overpasses, bridges, sewer and stormwater drainage pipes, building foundations, even basements require a lot of maintenance if they are unprotected initially. What are the environmental factors that corrode these structures? And there are several, and we will go through them. Underground soil corrosion. Untreated or buried non-reinforced and even metal reinforced concrete possesses an extremely high risk of corrosion. The physical characteristics of the soil play a part, and this is particle size and distribution. The chemical makeup of the soil, that is pH level. Is the pH acid or alkaline in nature? And then the presence and concentration of certain water-soluble salts, such as chlorides and sulfates. These water-soluble salts lead to direct chemical actions on the concrete itself. This can be on the exterior or the interior of the affected structure. The moisture content of the soil. Generally, high moisture equates to a growth of corrosive producing materials. High moisture levels provide a very suitable situation for the growth of fungi, bacterial infestations, if you want to call it that, and mold and mildew. The electrical resistivity of the soil is often very aggressive. This comes into play more when you are dealing with a reinforced structure. So this will be one of the things we will cover in our next information series. The soil aeration. Anaerobic bacteria, and by that I mean bacteria that thrive in low oxygen environments produce sulfides as byproducts, which have a very detrimental effect on concrete. Bacteria live in most, if not all, soils, but properly aerated soils do not provide the conditions that promote accelerated corrosion. Just keep in mind that poorly aerated soils can tremendously affect corrosion in a very negative way. Liquid immersion corrosion is something we need to touch on. Water is known as a universal solvent. It is very polar to such things as corrosive salts and can possess a low resistivity, leading to structure corrosion itself. There are two types of liquids that we need to think about. The first is what is called aqueous liquids. These are liquids such as water, which is the most common liquid involved in corrosive situations. The other is known as non-aqueous liquid, and these are high concentrations or moderate concentrations of such things as alcohols or other chemicals. But these also can facilitate corrosion. Biological activity can be very pronounced. This will tend to accumulate on concrete pipe surfaces, which can be on the exterior surface or the interior, and even in the interstices of the structure itself. Once these colonies are formed, they can infiltrate this porous concrete and escalate the corrosion process. This is particularly detrimental in wet or moisture-laden surroundings where there is a lot of unprotected concrete structures, because they fall very easy prey to bacteria, molds, fungi, and mildews. In liquids, pH plays a very major role. An acidic pH is something in the neighborhood of 1 to 6.5. Neutral, neither acid nor alkaline, is around 6.5 to 8. And then alkaline, which concrete is alkaline in nature to begin with, falls somewhere between 8 and 14. Acids and alkali can cause severe damage by breaking down covalent and hydrogen bonds in the concrete. Acid alone promotes a lot of bacterial colony growth. Very small changes in pH can have a very profound negative effect on concrete corrosion. There are other factors involved with liquid-induced corrosion. Very briefly, these are the system configuration. That is the exposure of the concrete surfaces to liquids and vapors, drainage, and the type of flow. Is it active or passive? The liquid chemical makeup, the types and concentration of dissolved substances, and its resultant pH. The flow rate. High flow rates tend to increase the exposure of a reactant to the concrete and increases corrosion. In unprotected concrete piping or structures, the effect of temperature can be very complicated. In high temperatures, tend to yield higher corrosion rates, and this is due to its increasing ion diffusion in the liquid itself. Higher temperatures, but also on the other hand, and the reason I say complicated is that higher temperatures can reduce the gas solubility, which reduces corrosion. Higher temperature can cause the scaling from deposition of soluble materials. Gas solubility in liquids can be increased with a higher pressure, and this pressure can stress the concrete structure joints and its physical integrity. Then finally, this last factor we've touched on already, and that is biologicals. Biologicals produce very corrosive materials as a byproduct and can rapidly disintegrate concrete. Atmospheric corrosion is the oxygen content that is important in this type of corrosion. However, there are other constituents that are important and contribute to this. Gases. These gases can result and lead to acid rain and also sulfur oxides. Temperature again. Higher temperatures tend to promote corrosion. There's also a question in certain areas of the country of industrial byproducts that tend to leach into the water table or tend to wash into the mainstream of effluent. Higher levels of corrosive gases such as sulfur dioxide from these industrial byproducts will lead to acidic water. Solids, and these are such things as salts, and these are very prevalent in coastal areas. Liquids. Higher moisture on surfaces will tend to lead to higher rates of corrosion. Especially when the concrete itself is constantly exposed to tremendous amounts of moisture. Tropical conditions. This is generally represented by such things as increased humidity, which leads to an increase in different types of fungal growth, as well as bacterial growth, mold, and mildew. Then there are marine conditions. In marine conditions, you have a high level of dissolved chlorides, salt, that deposit themselves on the surfaces of concrete infrastructures. Once deposited, these structures tend to remain wet longer when they are exposed to moisture. Then there are rural conditions that occur, especially in the area of the country where AIS and MarMac is located. You tend to get a lot of accumulation of dust and fertilizer overspray, which tends to coat infrastructure materials. This contributes to prolonged wetness once that structure has been dampened. What are some other factors of corrosion? Industrial waste, such as slag and corrosive gases, microbes in sewer pipes. When these start forming, they tend to form colonies or layers, creating a more toxic environment for corrosive compounds to form. This microbiologically induced corrosion, also known as MIC, M-I-C, can be greatly increased in these pipes by slow flowing, low flowing, or standing water in an unprotected infrastructure. This type of corrosion can involve the interior, exterior, and interstices of the structure itself. Let's move now to some fast facts. Chemical and/or mechanical factors can contribute to concrete corrosion, especially when the structure is unprotected. In areas of the country, structures experience severe freeze-thaw cycles. This can degrade concrete as well. Because concrete is porous, it allows the ingress and moisture vapor transport of liquids, predominantly water, and repeats itself through the season, especially in the wintertime, where you suffer from very cold, freezing evenings, and it warms up during the day and thaws. These are what are known as freeze-thaw cycles. Road salt and de-icing chemicals, especially in areas like the Midwest, can contribute to severe corrosion. Aggressive chemical exposure can cause very rapid corrosion of concrete. As we've seen earlier, acidic pH environments can have a devastating effect on the corrosive effect of concrete, as seen in the corner of this slide. This was a solid piece of concrete that was exposed to sulfuric acid with a very low pH for a short period of time, and it totally destroyed the covalent and hydrogen bonding of the concrete itself. Soil moisture can lead to bacterial growth and contribute to very profound pH variations. Erosive particles. These can be solid particles that are carried via the wind and even by water, can compromise unprotected concrete surfaces. Hard and soft water have dissolved salts in them and can be of extreme pH levels. This contributes to the degradation of concrete as well. Underground concrete can suffer dramatic corrosion from the soil environment. The environment of that soil can change in very short lengths along the path of underground concrete. Pipes, septic tanks, drainage structures, even piers and footings are typical examples. So what can we do to prevent corrosion? Well, we can take measures that extend the useful life of concrete, and that's exactly what we've done here at AIS. Concrete admixtures that can be added to new structures as they are made and allowed to cure, which can help prevent and retard corrosion. Two such admixture products. One is AMX 5500. It protects the concrete by limiting the bacterial and fungal growth. AMX 1000 is a very effective moderator of freeze-thaw occurrences and reduces the permeability to water and increases the concrete's resistance to surface cracking and fissuring. There are also protective treatments that we can use. These can be applied to either new, after curing of course, or existing structures. And the use of these protectants prevent the ingress of water into the structure. They essentially serve as a barrier. One such treatment is TST 4300 surface treatment. This protects by resisting the moisture intrusion into the structure itself and reduces the growth of mold, mildew, bacteria, and fungal activity. And And then lastly, there are surface coatings. These can be applied to new and existing structures, and they create a more impermeable barrier, protecting the exterior of the concrete infrastructure from corrosive environments. One such product is our PSC 2300 series of polymer coatings. It creates a water and chemical resistant barrier while limiting the bacterial and fungal growth that it is exposed to. It is weatherproof. It resists UV light degradation, and being such a thorough exterior coating, it also resists the friction and wear. Some few of the properties of PSC 2300 are its excellent chemical resistance. It has a very low moisture permeability, is very easy to apply, has outstanding adhesion. It's tough yet flexes enough so as not to crack and break away, and it is temperature resistant. So why did AIS develop PSC 2300 series coatings and other coatings? MarMac, our parent company, has a 70-year reputation for being a cutting-edge innovator in the infrastructure arena, and our pipe couplers outlast the pipes themselves. The major advances that the industry has seen has been in the area of waterborne chemistries that replace solvent-borne chemistries, which tend to be less green, more harmful, and require more thorough cleanup and more care. We developed it with green chemistry in mind, sustainability, waterborne versus solvent-borne materials, lower VOCs, little to no APEOs, and it is inert when it's cured at ambient temperature. And the chemistries on the whole tend to be simpler and less and take less time to cure and do exactly what they were intended to do. There's minimal PPE required, very easy to apply and clean up, neutralized with water. We can tailor most of our coatings to a customer's specific needs. Should they need a coating that is more chemical resistant, less water resistant, we can do that. And it is very compatible with today's needs and requires no activators. So our final thoughts are this. MarMac AIS is focused on improving and prolonging the useful life of concrete infrastructures of this generation and beyond. Our R&D and technical staff are available to you. Feel free to contact myself or any other technical representative with the company, and we will address your needs. We will always try to offer cutting-edge chemistry solutions to meet your requirements. And finally, we thank you for joining us today, and we hope that you have found this informative, educational, and useful. We look forward to presenting more info series as we progress along. Thank you.